Maybe it's
Feeling
more
about
for
derivatives? I had during math lab yesterday drawn a complete blank on what derivatives were.
So let's, okay, yeah, let's do a little refresher. So remember that the derivative, I guess I should call it review. Oh, and I know we talked about there's only really a few of us, and I forgot to make quiz 5, so it's not going to be available right after class. It'll be available sometime this afternoon, and it will just be on 3.1 and whatever we get through today. So quiz 5. Hopefully no one was.
I didn't do so hot on the last quiz.
Yeah, it looks like I need to go in and because I looked at your work, like your guys' work in general, and the work looks reasonable. So I'll go in and kind of make some adjustments to
Oh,
those
thank you.
marks. As I saw, yeah, there was when it's straight like right or wrong, then yeah, your grade's gonna be low most of the time. So I'll go in and adjust that. But yeah, so I'll make some.
Thank you, Carly. It makes me feel better about my 33% I got.
Yeah, so and there was a lot on there too. Yeah, I know, it's nice to know that you're not alone. So don't worry. So quiz number 5 will be available this afternoon. Sorry about that. And Carly was the one who told me that I had managed to forget to make a grade scope for quiz 4. I'm really dropping the ball on these quizzes. So I whipped one up quickly. Nobody noticed, I think, besides Carly.
That might have been because I ended up doing them afternoon Friday, the quiz and the assignments, and I was up until 11:30, which might have had something to do with me getting such bad marks on the assignments as well. I'm going to try to turn this into a learning experience. Exactly. As in, don't do that.
Yeah. Hey, easier said than done. Totally. Okay, so it'll be available this afternoon, I promise, and it'll be on 3.1 and up to the end of today, wherever we get to. I'm hoping to get well into 3.4, which is on the chain rule, because then we'll have a really good roster of derivative rules. So let's do just some quick review, right? A reminder about the derivative. The derivative, right, is the slope of the tangent line at some point x. So the derivative, f prime of x, is the slope of the tangent line on the original function f of x at x. So it's the slope of the. Hey, it's not just 3 of us anymore. Now there's 4 of us. I don't know what to do with myself. Okay, so the derivative is the slope of the tangent line on some function at some value x. So we were using the limit, but now we've moved away from the limit and we're just developing some rules. And last day, let me go grab them. In the 3.2 notes, which we'll get through today, at the bottom, there's this full table of differentiation formulas. So, we've got through, right, so just as a reminder here, the derivative of a constant is 0. And if you think about a constant as a function, right, a constant as a function is just this horizontal line. So it makes sense that the slope of the tangent line would be 0, right, because there's no rise. We also said that, okay, if I have some to the power of n, right, then what we do is we bring that n down in front and then we decrease the power by 1. Even if the power is negative, right, then we still decrease the power by 1, which might, require a little bit of thinking, but not bad. We also developed that the derivative of e to the x is just e to the x, which is kind of a cool property of e to the x. Okay, what does that mean? It means that if you have e to the x as a function, right? So if we think about e to the x as a function, let's just draw it here. Whoop. E to the x. Then the slope of the tangent line at any value of x will also be e to the x, is what that's saying, right? The derivative of e to the x is e to the x. So the slope of the tangent line at some point x, any point x, is just e to the x. Okay? So that's kind of a cool property and something to have up our sleeves. So then we branched out a little bit and we said, okay, if I'm multiplying by a constant, the derivative is actually only on the function. So it's only with respect to x. So only f has x's in it. So if you're taking the derivative, you're only taking the derivative of x's, right? Because the derivative of a constant is 0. So you can bump that constant outside and then just take the derivative inside. Then we had the sum of the derivative is just the sum of the two individual derivatives, right? So here's where we kind of branched out and we said, okay, well, now I'm able to deal with a polynomial, right? Because a polynomial is just sum to the power of n. There could be constants out in front, but then you just kind of bump inside the constants or inside onto the function. And then you can just take the derivative of each little term in a polynomial. So that's kind of where we ended off. And then just to kind of get you started on the next section, I also introduced the product rule, and maybe, yeah. So this is called the product rule. And this is called the quotient rule. Quotient is just division. So I write these in different order. So for me, maybe I'll just do, I write the product rule as, so fg prime. So I'm multiplying some function f times some function g. So the hard part is not finding the derivative anymore. It's going to be identifying these functions. And that's going to be kind of the hardest part of this chapter, is figuring out what is this function made up of. Is it two smaller functions being multiplied together? Can I rewrite it like that? Or is it maybe a quotient of two functions? Right? And so I actually rewrite this because I like to have patterns for myself to kind of memorize stuff. And so if I have something plus something, a plus b is the same as b plus a, right? I think we can all agree. And so, and then a times b is the same as b times a. So I can change the order inside each of these terms, and I can also swap them. The reason I want to do that is because I want to rewrite this as f prime g plus f g prime. I like to have f, and then g and g. So see here, right, I take the derivative of f, and then I multiply it by g, just g, the original function. plus just f held steady times the derivative of g. Okay. I like to have this pattern because if we go to the quotient rule, here I also have f prime g and then minus fg prime, right? So I like to have that same pattern because then otherwise I get so worked up on trying to memorize these individual patterns, right? But if I can make them all look the same, then that's easier for me and hopefully for you too. So you can absolutely use this, right? I think we can all agree that fg prime, right, is here, and gf prime is here. Those two being added together, it doesn't matter if I do a plus b or b plus a, you end up at the same place. Subtraction is different, right? So a minus b is not the same as b minus a. So here, right, I'm taking the derivative of f first and then multiplying it by g, and then I've got minus f held steady times the derivative of g, and then I'm dividing by g squared. We're not going to worry about where that came from. Of course, we could prove it, but we're not going to. We're just going to use it. And so I like to write the quotient rule. And the quotient rule as, so I've got f over g prime is also f prime g minus fg prime over g squared. So again, I'm taking the derivative of f first and then holding the f steady and then holding g steady and then taking the derivative of g. Also noticing that here I'm adding and here I'm subtracting in the quotient rule. So that's how I like to think of these. But if you find that's confusing, then absolutely, there's no harm in using these ones, right? So I would probably, if you have some sort of cheat sheet going on, then definitely have these formulas on there. In fact, you might have already memorized the first 6, right? The ones from last day, because they're kind of intuitive, whereas the product rule and the quotient rule are not that intuitive, right? I wouldn't be able to develop that just in my mind. But if I tell you that, okay, if you're adding 2 functions and you want to find their derivative, then you can just add the derivatives. Okay, I'm okay with that. That makes sense, right? Same thing with subtraction. So definitely have kind of the product and the quotient rule available. So I introduced the product and the quotient rule just so you can kind of stew on it for the weekend, or set it and forget it. Doesn't matter to me. But let's just introduce it properly. So we'll call that the end of our review. But definitely have the product and the quotient rule ready. So 3.2 is on the product and quotient rules. We're going to go a little bit, there's not a lot that I've included in this section because the product and the quotient rules are going to come up again and again and again. So we're going to keep using them. So we don't need to have, examples, tons and tons of examples in this section because it's going to haunt us forever now. And same thing with the next section where we talk about trig functions. So they'll come up. So we're just going to introduce them here and then we'll move on and we'll just use them. So unlike sums and differences, the derivative of a product or a quotient, the derivative of a product slash quotient of functions will not be the product or the quotient of the derivatives, right? So that's what we established. Functions will not be the product or quotient of the derivatives. Oops. Let's look at the official product rule, okay? Because I used prime notation, which is totally fine, and that's how I do it in my mind. But I mean, technically what's going on here is d dx of f of x times g of x is, and then here we could rearrange this to match our prime notation, right? And so I'm just gonna bring in this whole thing, and let me just mark it up so that it moves to the top. Okay. And then here I'll say or, right? Like we said earlier, I like to have f prime g plus f g prime. And just kind of take a second to convince yourself that those two are the same, right? There's nothing. Yeah, so you can absolutely just use prime notation. That's fine. There are a couple of instances where you would have to use the ddx, and I'll show you where it's actually easier to use the ddx. But yeah, use the prime notation. I get it. It's really annoying to use the differential operators. And it's not until now, to be honest, that I'm okay using them. And I have my calculus saber, which is Calc 4. So done tons of calculus, and I still hate differential operators because they make it look so nasty, but sometimes we have to use them. So I'm slowly surrendering. Okay. Definitely use the prime notation. Okay. So the product rule technically looks like this, but if you want to use prime notation, I would probably, I'm gonna lean towards this order, but if you want to use this order, that's totally fine. So what does this thing look like? Let's do an example. We'll start nice and slow. So if I have x to the x, and maybe I'll make this a little bit bigger. If I have a function x e to the x, right, the key is to really take your time and figure out what's happening in my function. How can I break this thing down? And so here I see that I have a function x times a function e to the x. And so what we have is we can say, okay, well, f of x equals x e to the x. So here, even though this function is also called f of x, just to match the notation of the prime notation that we developed, I'm going to call this f, and I'm going to call this maybe orange, call this g. Okay. So the hard part is recognizing that you have a product, right? So here we need the product rule. Mm-hmm. Whether you want to find f prime and g prime individually and then just kind of knit things together, that's fine. We're going to start kind of moving in the direction of doing it all in one go. So I'm gonna just go for it. So f prime of x, we just established is f prime g plus f g prime. One thing that I will say is the reason that they have the primes as the second term is because otherwise you might get confused and take the prime of the first one and the second one or something like that. But as long as you keep it straight in your head, it's okay to kind of change the order. So, okay, f prime is going to be what? The derivative of x is just 1, right? X to the power of 1. Technically, I bring the 1 downstairs. And then I take x to the power of 1 minus 1, x to the power of 0. Anything to the power of 0 is 1. Or I'm pretty sure it's on your, oh, it's not on in the table. That's okay. We know that the derivative of x is just going to be 1. Let it catch up here. So slow. So here, right, f prime is 1. G is just e to the x. So we just keep it there. It gets confusing because we also know the derivative is e to the x, but we'll deal with that when we get there. And then plus f, which is just x. And then g prime is e to the x. Right? So here I will make a note that f prime is 1 and g prime is e to the x. Right? So if you want to kind of do them over on the side and then plug them in, that's fine, that's great. But either way, you're going to end up with something like this. I see that I have a common e to the x, so to simplify things, I'm going to pull that outside. So I have e to the x times 1 plus x. Okay. How about we do another example? Example 2. We want to differentiate the function f of t. So this tells me what my function is with respect to. So my function is with respect to t, meaning that a and b must be constants, right? And so function is with respect to, so usually we write WRT with respect to t, so a and b are constants. Maybe I should put this all on fresh page. Okay. So if I want to take the derivative of this thing, right, I've got the root of t, okay, so that's a function of t, and then I have a plus bt, which is polynomial with respect to t, right? And so I'm able to break up this function. F of t is the root of t times a plus b times t. So again, I'm going to call this my f function and this my g function. If I want to find the derivative of f, well, f is the root of t, and but by the context, because I've labeled this f, you're not going to get confused with f of t. That's different. That's the overall function. So a little bit dicey, but so here, actually, let's just write it normal. The root of t, last day we talked about, okay, so often it's going to be beneficial if we just rewrite it as an exponent, right? Especially if we have roots. And so this is the same as t to the 1/2, mostly because we have that exponent rule where we bring down the exponent and then decrease it by 1. And so, so this is f. So f prime is 1/2 t to the 1/2 minus 1. Which 1/2 minus 1, technically you need a common denominator, or you might just see that it's negative 1/2. So then you get 1/2 t to the negative 1/2. G, we don't have to manipulate G, but G is a plus B times T. So G prime, if we kind of do them separately, is going to be A is a constant. So the derivative of A goes to 0, right? And then B times T, well, the derivative of T is just 1. Oh, do you mean this? So this is the derivative of an exponent. So that's from last day. So you'll want to brush up on that because we need it. Awesome. So then if we have to take the derivative here, then the derivative of A is 0, and then B times T is just going to be B. So now, if I take the derivative of f times g is f prime g plus fg prime. But I already solved for most of these, right? And then I'll put them together and I'll be able to simplify. So I have 1/2 t to the negative 1/2 times g, which is a plus bt, plus f, which is the root of t, times g prime, which is b. Oops. Okay, good. So you can kind of regroup things, try to simplify maybe a little bit, noticing that t to the negative 1/2 is the same as 1 over the root of t. So I think what I'll do is I'll bring that root of t downstairs. So then I get a plus b times t over 2 root t plus the root of, and maybe I'll bring that b outside, b times the root of t. I'll need a common denominator, so I'm going to multiply by 2 root t on that second term, 2 root t over 2 root t. So then I end up at a plus bt plus 2bt. Root t times root t is t over 2 root t. Putting me at a plus 3bt over 2 root t. A little bit of simplification going on here, but not bad. One thing that can be a little bit of a time saver is if you are able to rewrite something as a polynomial, because we know polynomials are easy to find the derivative of, then that's always my go-to, right? Can I rewrite this as a polynomial? So if you have a look at this function here, if I multiply or expand this root t inside, then I could rewrite this as a polynomial, and then it's a lot easier. What we'll find is that we end up in the same place. So it doesn't matter, but there sometimes will be easier and harder ways of finding the derivative. If you're kind of keeping your cool, you'll end up in the same place regardless, right? So it doesn't matter, but sometimes it will be easier to differentiate a function, if we manipulate it first. Right, so if we think about f of t is the root of t times a plus b times t. If I expand that root t inside, I get a root t plus b root t, bt root t, let's write it that way. Which we can rewrite as t to the 3 over 2, right? T to the power of 1 times t to the power of 1/2. 1 plus 1/2 is 3 over 2. This becomes a times t to the 1/2 plus b times t to the 3 over 2. Right? And so now I'm at this nice polynomial if we can rewrite a polynomial, as a polynomial, we can avoid the product rule. I will make a note here that we will arrive at the same answer regardless, right? One is just a little bit more work. So we will arrive at the same result regardless. Because now, if you take the derivative of this polynomial, so f of t, I'll just jot it down here as a to the t to the 1, or a times t to the 1/2 plus b to t to the 3 over 2. So f prime of t, now it's just a polynomial, right? So I need to bump the constant outside, and then I can take the derivative of t to the 1/2. And then same thing with the b, I can put outside and take the derivative of t to the 3 over 2, putting me at a times 1/2 t to the negative 1/2, sounds familiar, plus b times 3 over 2 t to the 1/2. Right, 3 over 2 minus 1 is 1/2, yeah. This, after some massaging, we're not gonna get there, but but after some massaging, this becomes the same as what we found earlier. After some massaging, as what we found earlier, right? Common denominator is all that fun stuff. So, good. So that's just something to keep an eye out for. And because I'm lazy, it's something that I tend to spot quickly, right? Can I rewrite this as a polynomial? Because taking derivatives of polynomials is quite simple, right? Once you kind of get into it and get the hang of it. Everything else is a little bit harder. So if I can get to a polynomial, then I'm happy, right? Sometimes or quite often actually, it's just going to make a bigger problem if you expand stuff out. So it's not unless you see an obvious polynomial kind of emerge that I would do the expansion, but it is a good trick to have up your sleeve if you want to avoid the product rule. So good. Let's talk about the quotient rule then, right? As long as we're able to recognize a quotient, and the quotient rule, at least for me, is a little bit easier to spot just because, well, you have to have division, right? So if you have a function over a function, then you need the quotient rule. So if our function can be rewritten as a quotient of two smaller functions, inevitably, right? Or not necessarily rewritten, but it can be read or rewritten or read as a quotient of two smaller functions, we need the quotient rule to take the derivative. We need the quotient rule to find the derivative. So I'll bring in the official quotient rule, and then, but we'll also look at the prime notation, and I'm gonna reiterate how I personally like to write the quotient rule. Right, so here, or if you're finding the derivative of some function f over some function g, right, of course you can use the d dx notation, right, differential operators. We'll stick to prime notation, especially if I'm, so what you'll find is when you're plowing through all these derivatives, sometimes if I need the quotient rule, I'll just jot it down in the margin somewhere and just kind of have it and reference it, right? So then I'll definitely use prime notation. So to match the product rule that we just established, I do f prime g minus fg prime over g squared. Right? So that's just me personally. And like I said, it's nicer to have the derivatives on the outside because then there's no question about what are you taking the derivative of. But I think as long as you can kind of keep them straight, then you're safe. So let's see here. Let me just check. All right. Let's just get right to it. Let's do an example of the quotient rule. Do it on its own page here. Okay. So like I said, picking up on having to use the quotient rule is a little bit easier than the product rule sometimes. So here, right, I see that I have a polynomial over a polynomial, right? And so I need to use the quotient rule. So I have a polynomial over a polynomial. Therefore, need the quotient rule. In fact, as long as you have a function over a function, then you'll need a quotient rule. Right? Okay, so, and maybe I should emphasize that I have a function over a function, and it happens to be a polynomial over a polynomial. So that's why we need the quotient rule. Okay, so, right, just remembering, okay, the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared, that's going to take some work, right? And so, like I said, I like to kind of just jot down the quotient rule somewhere so that I can see it and just kind of map to it, right? And here, just kind of have it with you everywhere you go. No, not necessarily. Maybe. Okay, so what we want to do is we want to find the derivative of y. So y prime, let me just go there, make sure. All right, so we know y prime is, and maybe I'll just move my quotient rule down here. It's f prime g minus fg prime over g squared. And I'll just make a note here that this top one is f, and x to the 3 plus 6 is rg. So you'll want to make sure that you use your brackets pretty consistently, right? You want to use it. More brackets is always better than not enough brackets, right? And so sometimes I go a little bit overboard, or sometimes a lot overboard with my brackets, but they're just for me to keep things straight. So if I take the derivative of f, so x squared plus x minus 2, that's a fairly easy derivative to find, right? It's 2x plus 1. Same thing with x to the 3 plus 6. The derivative of x to the 3 to the plus 6 is just 3x squared, right? The derivative of 6 goes to 0. So now I can put those together, and I get 2x plus 1. That's the derivative of f. And then g is just held steady. So x to the 3 plus 6 minus, and now f is held steady, x squared plus x minus 2 times g prime, which is 3x squared, all over g squared. So not the derivative, just g as it was, x to the 3 plus 6 squared. Most of the time, I'm not going to do anything with g squared. It just stays g squared unless I'm able to pull out a common factor of g and cancel it maybe, but that's going to be pretty rare. So usually I just end up keeping the g squared, just holding it, even in my simplification. So what I can do though is I can expand. So now we're just back to normal math, right? And so now I can just simplify the numerator by expanding, and I'm going to bump it over just a smidge because it's going to expand to be quite large. Oops. Helps if I line up the lines there. 2x times x to the 3, right? So now we're just expanding. So I get 2x to the 4 plus 12x, and then plus x to the 3 plus 6 minus, I'm going to keep that negative outside and expand it in at a later step. So I get 3x to the 4 plus 3x to the 3 minus 6x squared over x to the 3 plus 6 squared. Okay, this becomes, I'm going to expand this negative inside here, and let me just make sure. Okay, 2x to the 4 plus 12x plus x to the 3 plus 6 minus 3x to the 4 minus 3x to the 3 plus 6x squared. All over x to the 3 plus 6 squared. Now I can go ahead and simplify here, so I get negative x to the 4th. I like to cross stuff off as I'm able to cancel them and kind of group like terms, just for, it's easier to see. X to the 3.
Quick question.
Oh, sorry,
yeah. 6x to the 6?
No.
Okay, good. I'm not going insane.
Squared. Right, 6x. Yeah, sorry about that. I was stuck on my 6's. Good catch. Would have made a real mess. Get x to the 3 minus 3x to the 3 puts me on negative 2x to the 3. Now plus 6x squared plus 12x plus 6. Let me just make sure that I did that. Matches what I have here, so that's good. Okay. So let's do that that last example on this handout, unless you have questions about that one. But I feel like you caught my typo, so otherwise there'd be questions about that. No, I wouldn't bother expanding the denominator because it's not going to let you cancel unless you have common multiples. And I don't see any common multiples really here from all of these terms, so nah. Usually I just let it hang out, g squared. So yeah, you can, but no worries. I just leave it. So you can too. Okay, so I wanted to do one of these examples where we again find the equation of the tangent line. It feels like all we're doing is finding the equation of the tangent line, but that is all we're doing basically in this whole course. So especially if you're working through the labs, right? They love to make you find the equation of the tangent line. There you'll use Maple to find your derivatives, right? But the idea is the same. So let's find the equation of the tangent line to y equals e to the x over 1 plus x squared at the point 1 and 1/2 e. So here we have y equals e to the x over 1 plus x squared. And we want to find the tangent line at 1 1/2 e. And you can just confirm. So here, what we're saying is at x equals 1, we can confirm that y should be 1/2 e by putting in x equals 1 here, right? And so when x equals 1, y equals e to the 1 over 1 plus 1 squared, which, to keep it on the same page here, is e over 1 plus 1, which is 2, so e over 2, or 1/2 e if you prefer, right? And so that's where this came from, this 1/2 e. I only bring that up because sometimes it throws people off, but it is just the y value evaluated at that value of x, right? So it is just an ordered pair. Okay, so we have a point. Okay, so remember, to use our point slope form of the line, we need the slope, right? And so we have the point. We have the point 1 and 1/2 e, but we need the slope. But we need the slope at x equals 1, right? And at x equals 1, because it's at that point, x equals 1, y equals 1/2 e. So what that says is find the derivative, right? Because that is the slope of the tangent line. Find the derivative at x equals 1. So what we're going to do is we're going to find the derivative and then evaluate it at x equals 1. Okay, so I'm going to jot down the function here, y equals e to the x over 1 plus x squared. It's catching up. Okay. So y prime, and just to kind of ease into d dx notation, right? So then the derivative with respect to x, d dx of y, or if you wanted to write dy dx, that's fine, is going to be the derivative of the top times the bottom minus the derivative of the bottom times the top, or whatever order you want. For that last one, I didn't stick with my original. Over the bottom squared. So I have e to the x times 1 plus x squared minus, right? Because I've got a quotient here, so I need the quotient rule. There's no simplification that I can do. Rewriting this, I'm just going to go for it. So then minus e to the x times 2x over 1 plus x squared squared. You don't want to forget that squared. That was probably among my number one mistakes that I would make, is forgetting to square the bottom, which is not good. It's pretty bad. But we all make mistakes. So I can expand this out and simplify, right? So I get e to the x plus x squared e to the x minus 2x e to the x. Kind of writing it out a little bit nicer. Over 1 plus x squared squared. This is, I don't really see anything that I can cancel. I could pull out a common e to the x, but I'm actually just going to leave it because I want to evaluate this at x equals 1. Right, so this is the general tangent line at any value of x. So this is the tangent, or sorry, the slope of the tangent line, I should say. The slope of the tangent line at any x. Okay. So we need to evaluate dy dx at x equals 1, right? Because we want it at that very point 1, x equals 1, y equals 1/2 e. How do we show that? So we have a way to show that, because remember before, if I said, well, f of 1, well, that's the function f evaluated at x equals 1. And so especially if I've used dy dx notation or d dx of, you can squish them together, pull them apart, doesn't matter. How we denote that is we say dy dx, and then a straight vertical bar means evaluated at, and then kind of down in the bottom here at x equals 1. So this you're going to read dy dx evaluated at x equals 1. So that's new notation, but it's just something to kind of have in mind. Okay, so then this becomes, I have the derivative, so now I'm just going to evaluate it at x equals 1, right? And so I have e to the 1 plus 1 squared times e to the 1 minus 2 times 1, e to the 1, lots of e's to the 1, over 1 plus 1 squared, all squared. The numerator becomes 0, right? E plus e minus 2e, but let's just 2e minus 2e over 1 plus 1 squared is 2, and 2 squared is 4. So then I get 0 over 4. Which is just going to go to 0. What does this mean? If I find that the derivative at that value of x is 0, we've called that a horizontal tangent line, right? Because then I have a slope of 0 at that point. So here, this says that we have a horizontal tangent line at x equals 1, right? Not necessarily all over. We know this thing's going to vary, but just as a very specific value of x equals 1, we have a horizontal tangent line. So that's okay. Slope is 0, right? So we can still use the point slope form of the line, right? And so the equation of the tangent line or any line, let's just do the general point slope form. Y minus y naught is m times x minus x naught. Y minus, it was, the y value is 1/2 e, is the slope, which is 0, okay, x minus 1. 0 times anything is just a 0. So then y equals 1/2 e. Which makes sense, right? Because y equals 1/2 e. E is just some number, right? And so e divided by 2 is still just some number, some constant. And so we have horizontal tangent line at x equals 1 and y equals 1/2 e. Good. Do you guys want to break today, or do you want to end a little bit earlier instead? Decisions.
A 5-minute break would be useful so I can get a little bit more printer paper.
You got it. So let's do a little break until 11:08. We'll do a 5-minute break. Until 11:08. All right. So that's all we're doing for that section. But of course, the product rule and the quotient rule, like I said, they're just going to haunt us for the rest of the term now. So it's worthwhile spending some time kind of maybe even memorizing them. I don't know. It's crazy, right? Speaking of memorizing, your guys' tests are open book. So typically you would have to memorize all these derivatives of trig functions, but you guys can just have them available. But just know that you should be really quick to get them, right? So some of these you will end up memorizing regardless. But section 3.3 is on the derivatives of trigonometric functions. These are just things that you have to just kind of know or have available and just kind of be able to use. And so I don't want to prove any of these functions or any of these derivatives. You can, and a lot of the proofs are outlined in the textbook. And so we will not prove any of these derivatives. But if you're interested, I mean, they're in the textbook, or Khan Academy, I think, does proofs of all of them. I haven't checked recently, but if you're curious, they are in the textbook. Or on Khan Academy, of course. That soothing voice of Sal Khan. So I don't want you to prove them. I just want you to know them and use them. And so let's just bring in these derivatives. Oh, and I just updated the handout to include these fundamental identities at the bottom, which are actually from pre-calc, but we're gonna assume that we know all these, so I figured it was worthwhile to kind of bring them back as a refresher. So they're just at the bottom with the new one, and I had to write them out on mine because I had the old version, but that's okay. So if we're talking about derivatives of trig functions, you'll see here that even the textbook says, memorize this table. Oh, okay. But sometimes it's nice. Hey, you gotta memorize this. Okay, then you know what you gotta do at least. The derivative of sine x is cos x. The derivative of cos x is negative sine x. The derivative of tan x is secant squared x. Cosecant x is weird, negative cosecant x, cotangent x. Okay, that's weird. Same thing with secant, cotangent. These I would just have on some cheat sheet somewhere, right? But these three, right, are kind of core trig functions, might be good to memorize. And it's even got this little helpful hint here that all the co-functions have negatives in front, right? So cosine has a negative, cosecant and cotangent all end up with negatives out front, which is kind of definitely helpful when you're trying to remember, oh, is the derivative of sine, is it cos x or negative sine x? One of these is negative, right? So it just helps to remember. Okay. So here they are, we're just stating the derivatives. Just like we said, the derivative of e to the x is e to the x. Here we are again, just kind of stating, and now we'll just use these derivatives. Okay, so we're just going to use these and apply these as we go. So this one was not in the textbook, but I did want to go through it. So I wrote it in. The reason I wanted to do this one is because we have to break this down into some functions, right? So some smaller functions. So if I have f of x equals x e to the x cos x, what I'm seeing here are three functions being multiplied together, but I don't have a product rule for three functions. I only have a product rule for two functions. For now, what we're going to do is I'm going to say, well, cos x is kind of its own beast. Okay? And then how about I treat x ex as one function for now, right? Remembering that x ex is also a product, right? And so here we have maybe f, and then we have, and maybe I shouldn't use f because I'm going to use f in a little bit here. Let's say A, B, and C. Right, we've got three functions. So for now, treat this as one function, right, which happens to be two functions being multiplied together, which is also a product. Okay. So now I've got this product rule of x ex times the cos of x. Okay. So you want to kind of keep your wits about you in a way. So treat this as one function, which will require the product rule. Require the product rule as well. And so I've got a product times a product, and then break down the one function, it becomes a product itself. So you kind of have to work your way down. So remembering that the product rule says f g prime is f prime g plus f g prime. That's our product rule. So for now, let's treat this x ex as f and cos x as g, right? Because I don't want to do something like e to the x because I just introduced trig function, so I want to keep it as its own. It doesn't actually matter how you group them. The key is you just have to treat two of the functions as one initially. So if we have f is x e to the x, what I really need to do is I need to find the derivative of x e to the x. So let's use prime notation, even though I'm not too thrilled about it. X e to the x prime here, I'll make a note. We should, and maybe for the next one, should write d dx x e to the x instead of using that prime notation inside. But I've been where you are, and prime notation just is easier to read. So I'll keep it for now. But g is just the cos of x plus x e to the x times the cos of x, but the derivative of cos of x, which is the derivative of cos x is negative sine x. So you'll want to use that negative there. Times negative sine x. Okay. So now what I want to do is I want to focus on the next product rule, x e to the x. And then I'm going to expand and simplify a little bit, right? And so here, this becomes, so my f in this case is x, and my g is e to the x. So I get 1 e to the x, or 1 times e to the x plus x e to the x times cos x plus, oh, I'm going to bring this negative out front, just bump it out front, minus x e to the x sine x. Okay. I can expand a little bit. So I have e to the x plus x e, I say I'm expanding, but then I don't expand. E to the x cos x plus x e to the x cos x minus x e to the x sine x. You can leave it like this, or you can pull out a common e to the x, but that's all I'm seeing here. So just kind of up to you, but you can pull out a common e to the x times cos x plus x cos x minus x sine x. And that's about all we can do for that one. So like I said, as we get into more complicated derivatives that we need to manipulate later, I'm going to start using the d dx notation. But if you want to read it as prime, that's fine. Okay, let's do another example. Oh, wrong sheet. Well, I want to do an example that's not on here. Example 1b, let's call it. Just because I want to just remind you what that we can square these trig functions. So differentiate y equals tan squared x. Okay. Just because here, right, tan squared x, just as a reminder, all these trig functions, if they're squared, that's the same as tan x squared, right? So then I can rewrite this as a product rule, right? Tan x times tan x. So then really y is tan x times tan x. And this becomes a product rule. Could you Well, we don't have the chain rule yet. That's why. The reason that I'm kind of humming and hawing is because you have a kind of a power here, but because there's a function inside, we don't know how to deal with that until the next section. So when you have a function inside and you want to take the derivative, we'll have ways to deal with that, and it's called the chain rule, but we don't have it yet. So if I have tan x, well, f is tan x and g is tan x. And so I've got this kind of weird situation going on, but it becomes y prime becomes the derivative of tan x is secant squared x. Right? So the derivative of tan x is secant squared x. So we need to remember that. So it becomes secant squared x times tan x plus tan x times secant squared x, or however you want to write that, which puts me at 2 tan x secant squared x. So it may be helpful to remember the following identities. Right? So they're the ones that I put at the bottom here. Definitely things like sine squared x, or sine plus cos squared is 1, but also I find that we end up using the tan squared plus 1 is secant squared quite a bit as well. And for me, definitely knowing what tan x, what ratio tan x can be really useful. So those would be the ones that I would focus on if you kind of had to lock some in. But definitely if you just have this, again, if you just have it available and know when to refer to it, that's good. Yep. So let's do that last example on this handout here. And it's kind of a big one, so let's see here. So if you have some function, and notice, so now I have trig functions taking part in a quotient rule, right? But just kind of break it down. Okay, I see a quotient, so I need a quotient rule, and then I'll need to deal with those trig functions inside. But then it also asks, for what values of x does the graph of f have a horizontal tangent? Horizontal tangent is where the slope is 0. So this is where f prime of x equals 0. Right, so we want to find, well, first we'll find the derivative of this thing, and then we're going to set it equal to 0 and solve for the values of x that make it 0. Okay. So nothing to it but to do it. Here we go. So we want to break down f of x into a quotient of two functions. So f of x is secant x over 1 plus tan x. Right? And I've got f is secant x, and g, let's let it be 1 plus tan x. If I do on the side somewhere, right, might be useful to kind of jot down on the side what f prime is. F prime is the derivative of secant x, which if we go back, the derivative of secant x, slow, is secant x times tan x. That seems weird, but that's what it is. So, okay. So I write down secant x tan x, and then just remember that the derivative of tan x is secant squared x. Here we go. So the derivative of f is secant x tan x. And the derivative of g is 1. So the derivative of 1 is 0. And the derivative of tan x is secant squared. So now I can kind of put these together in the quotient rule. And so f prime of x is f prime g, oops, almost did adding, minus fg prime over g squared. So we can put these together and say, okay, well, I already found these individual derivatives. Now I need to kind of knit them together here. I'll use big brackets just because there's a lot of functions in here, right? And so I have secant x tan x, that's f prime, times g, which is 1 plus tan x, minus f, which is secant x, times g prime, which is secant squared x. Over 1 plus tan x squared. Okay. I am seeing a common multiple of secant x, so I am going to extract that and pull it to the outside in the numerator, right? So I have secant x times tan x plus tan squared x minus secant squared x over 1 plus tan x squared. Here's where things get a little bit expand your style. When I look at this, I see a tan x and I see a tan squared x, but then kind of in the back of my mind, I remember that I can rewrite secant squared as a function of x, right? So if we refer back to those identities, right, we said that secant squared x, secant squared x, I can rewrite as tan squared x plus 1, right? So that's going to be the key is using that identity, and then we'll be able to cancel stuff out, right? Not obvious, but with practice, you'll get there, right? But it's not something that I expect you to be able to see away. But if you're trying to simplify this thing, right, then your go-to should be, okay, I've got all these tans here, and then all of a sudden I've got a secant squared, but then, right, maybe, oh, okay, check out your identities. Is there something that you can do? You could also rewrite tan squared x in terms of secant squared. It might get you to the same spot actually, so it doesn't really matter, but just get creative, I guess. That's what I'm saying. So here, recall that the secant squared x is tan squared x plus 1. So we can make that substitution. So we get secant x times tan x plus tan squared x minus, and remembering to bring that minus inside all the way on tan squared x. So I get minus tan squared x minus 1, just so I don't have to write it out one more time, over 1 plus tan x squared. Tan squared minus tan squared goes away. There's nothing really I can do here. I guess you could, nope, you can't. There's no way I can cancel 1 plus tan x up here because I've got tan x minus 1. Even if I rearranged, I'd still have a rogue negative, right? So a rogue minus. So I can't cancel anymore. So I get secant x is tan x minus 1 over 1 plus tan x all squared. But wait, there's more, right? So here, okay, so we wanted to find the derivative, which is what we did. And then we want to find, okay, for what values of x does the graph have a horizontal tangent line, right? And so, okay, so the derivative, when is it equal to 0? What values of x are going to make this thing 0? So now we need to kind of take a step back and just remembering all the identities, or keeping in mind identities. Okay. So we have horizontal tangents. We have horizontal tangents when f prime of x equals 0. Got this big nasty function for f prime of x. So here I've got f prime of x, just going to rewrite it again, as secant x times tan x minus 1 over 1 plus tan x squared. In fact, I'm going to move this down to the next page so I can write around it. Okay. You can definitely, and I would make use of Desmos here, because to me, I don't know what the graph of secant x looks like right off the top of my head. I don't remember what it looks like, so I'm just going to graph it here. So you've got your functions, and I want to write my secant of x. Okay. It looks to me like the output here will never be 0, right? And that is the case, right? But I just want to convince myself that, okay, so secant x is never going to be 0. It seems to have this the same pattern over and over and over and over and over and over and over again, okay? So what happens is, well, then secant x is never equal to 0, right? And I'll make a note here, see graph, right? You can graph it and just kind of convince yourself that it is never 0. And now that we've used that once, it might be worthwhile to just kind of jot that down, right? Secant of x, okay, it's never 0. Because what we're looking for is when this thing equals 0. So the only way to make something equal to 0 is multiplying by 0, or having 0 work out in the numerator, right? The denominator can never make something 0, right? Because even if I'm by 0, which I can't do, right, it makes the function not exist rather than go to 0. So here, by elimination, right, the denominator oops, box there. There. This can never make the derivative 0, right? The denominator can't make f prime of x equal 0, right? There's no way to use the denominator to make something equal 0. Okay, so now I've got something that can never be 0 times tan x minus 1 over something that can't make things equal to 0. So my only hope is when tan x minus 1 equals 0. Then I'll be able to say that when tan x minus 1 is 0, then I've got 0 times secant x, whatever it is, over something. 0 over something is just 0. So we need tan x minus 1 equal to 0. Okay. So tan x minus 1 equal to 0 is really saying, well, when is tan x equal to 1? Now, easy enough for me to say, but I maybe kind of refresh on the unit circle, right? But remembering that tan x is sine x over cos x, where sine x is the y value and cos x is the x value, right? So just kind of going down memory lane here, you've got your unit circle. Maybe I should do it like that. And remembering that, okay, I've got kind of these 3 cutoff points, key cutoff points. And I've got x comma y is the same as cos theta sine theta. Okay. Now, the other two escape me, but here at theta equals pi over 4, I have root 2 over 2 and root 2 over 2. Or sorry, pi over 2? Now I can't remember. Root 2 over 2, I think.
The sheet I've got on my left says root 2 over 2.
Root 2 over 2? I should have remembered David has the unit circle on his wall. Should just ask David. Root 2 over 2, thank you. Okay. So the only time that you have, right, because if you think about, okay, so tan x is really sine x, and this is from that identities sheet that I just gave you, sine x over cos x. When is that equal 1? Well, it's equal to 1 when they're the same, right? So we need sine x to equal cos x, which just means we have to have the same xy value, right? And that only happens here and here, right? Otherwise, x is negative, but y is positive. And here, x is positive, but y is negative, right? And so here, at negative root 2 over 2 and negative root 2 over 2. This is not something that I would get you to do on a test. Maybe on an assignment where you have time and you can kind of go back, you can look stuff up, you can Google stuff, you can kind of work at it, right? But this is not a test type question, so just don't freak out too much, right? Okay, so then here, this is a distance of pi. Those are the only two values where tan x equals 1. So now it doesn't matter how many distances of pi you move, right? As long as you're moving even distances of pi, or whole distances of pi, I should say, not even, you'll end up where tan x equals 1. And so now tan x equals 1 at intervals of pi from pi over 4. So we say at x equals, and usually we start with the n pi, right? The intervals of pi from pi over 4, where n is an integer. So that's where we have horizontal tangent lines. There's multiple, there's actually infinite values of x. So these values of x have horizontal tangent lines. Did it. That's hard, right? Kind of took it to the next level, right? But it's good to have seen something like that, right? We kind of work through it. Before we go, I do want to introduce the chain rule, just like I introduced the product rule and the quotient rule, just so that we've seen it once before we kind of get into it. And so 3.4 is the chain rule. And it is kind of the last big time differentiation rule that we'll need. And then we're going to move into different techniques of differentiation. We'll introduce some more rules, but these are kind of the big players. Okay, so if you have a function like f of x, f of x is the root of x squared plus 1. Just looking at the handout here. Oh yeah, so here, this will be the quiz number 5. It'll just go up to 3.3. I won't throw the chain rule on. Good call. So what we have here is, okay, so I've got a function inside a function, right? So whenever you have a function inside a function, we need the chain rule. And so here I've got a function inside another function, inside a function. Okay. So we're going to need the chain rule. We need the chain rule to differentiate. Now the chain rule is a little bit kind of nasty to read initially, at least. Where is it? Bring it in. Don't worry, we're going to break it down. The first thing is, well, we need to go back to function compositions, right? So f composed with g is the same as saying, well, f is my outside function and g is my inside function. So step one is to identify the inside and the outside functions. So step one, identify the inside and the outside function. Right, so up here, if you have f of x is the root of x squared plus 1, well, if I let f of x be the root of x, the outside function, and if I let g of x be x squared plus 1, the inside function, and I know I'm down to the wire here, the chain rule then says, okay, if I've got an outside function with an inside function inside, right, then what we do is the chain rule says, okay, you're going to take the derivative of the outside, right? So you peel away, so you take the derivative of the outside, evaluate at the inside, and then you multiply by the derivative of the inside. So then if f of x is f of g of x, right, then f prime of x is f prime at g of x times g prime of x. This is the derivative of the outside evaluated at the inside. Derivative of the outside evaluated at the inside, right? Just talking about the inside and the outside, but their functions, times the derivative of the inside. Okay. So, okay. We'll leave that example for next day, but just try it, right? Try those other problems and just kind of try to identify the inside function and the outside functions and just kind of try working through those for Friday. All right, I know I'm out of time. But, if you have any questions, let me know. Otherwise, quiz 5, I'll post it this afternoon sometime. Sorry about that. And hopefully no one's chomping at the bit to practice. If you have any questions, let me know. Otherwise, see you Friday.
In that case, see you Friday.
Yeah.